Welcome, everyone. We have an audience on Zoom and an audience in the theater here, so we're making progress. I'm Paul Kroll, head of the School of Physics and Astronomy, and on behalf of the College of Science and Engineering and the school and the Minnesota Institute for Astrophysics, I'd like to welcome everyone, both here and online, to tonight's talk. Professor Loya Williams will be introducing the speaker shortly. I would just like to say that it's great to be back. This is, in fact, the first public lecture in the school in 18 or 19 months. All right, so congratulations, particularly those in the room, for being the pioneers. As we emerge from the pandemic, there's a lot going on in the School of Physics and Astronomy. In addition to our regular teaching and activities and various teaching and research activities in various areas of physics, there are two institutes in the school. The host of tonight's talk, the Minnesota Institute for Astrophysics, and also the Fine Theoretical Physics Institute. Right? And I bring those up because the host of tonight's talk is MIfA. We are currently scheduling some of our other major public outreach events for the next 12 months. I can tell you as of tonight that there will be a Van Vleck public lecture for the whole school that will be in April 20th, 2022. MIfA will host a Kaufmannis lecture. I do not know if that is scheduled yet. And then the so-called Edith and Irving Meisel lecture will be hosted by the Fine Theoretical Institute, and that will be held next fall, right? And we're contacting speakers, getting those things going. And of course, next summer, there'll be Universe in the Park. And I don't know when public viewing will resume, but we're really, we're on our way back from a very difficult 18 months. And we thank you for your support during that time. All right, so I think I'll now turn things over to Professor Loya Williams, who will introduce tonight's speaker.
Thank you, Paul. Yes, it's my great pleasure today to introduce Michael Coughlin, our speaker for the public lecture, Minnesota Institute for Astrophysics public lecture. And so Michael is the latest addition to our faculty. He's been with us for a couple of years, and we're very excited to have him as a part of our faculty. His area of expertise is gravitational waves and multi-messenger astronomy, which is a very young field and growing very rapidly with a lot of exciting results coming in the future and in the last few years. So Michael got his undergraduate degree at Carleton College, actually, so he's a local. And also he did part of his undergraduate studies at the University of Cambridge. And in both of those places, he concentrated on searching for gravitational waves using LIGO, the Laser Interferometer Gravitational Wave Observatory, and another facility in Europe called Virgo. Michael, after his undergraduate degree, he did graduate studies at Harvard using Vera Rubin Observatory, which is an 8-meter class telescope, which is very big. And he built a prototype calibration system for the telescope. Now, calibration may sound boring, but it's actually one of the most critical pieces to make a telescope work. If without calibration, all the data you get is useless. So after his graduate studies, Michael went on to accept a prize postdoc at Caltech, California Institute of Technology, and he continued working on gravitational waves and also the observable signatures, like astronomical observable signatures using the Zwicky transient facility. And for the last couple of years, he has been an assistant professor at our institute, and he's building a group working on gravitational waves as well as multi-messenger astronomy. And we're absolutely delighted to have him as part of our faculty. So let's welcome Michael.
Nice. know my place. Hi. Okay, so first of all, huge thank you to Paul and Lilia, especially Lilia, who just spent an hour and a half listening to me grading and judging my introduction to astronomy lecture. And now she's here for another hour and a half listening to me talk about multi-messenger astronomy. So big shout out to Lilia. And requests from the crowd. So because we have attendees on Zoom, I've been told in no uncertain terms that if I wander to my left here, as I may be prone to do, they will not be able to see and or hear me at that point. So do not feel afraid to, just, move me back, to the lectern where I belong here. Very kindly, Lilia introduced multi-messenger astronomy with gravitational waves a little bit. And my hope today is to try to convince you that this field, which we'll learn about together, really is the cool thing to be doing these days in astronomy. But to get started, historically, astronomy observations are made with different kinds of light, right? And so I can take measurements across the electromagnetic spectrum. So here I show a plot or images of a particular galaxy, X-ray, UV, visible, mid-infrared, and the radio. And throughout much of astronomy history, astronomers have been predominantly studying objects of this kind in what I'd say single messengers. I am personally predominantly an optical astronomer, so I use a mix of visible and UV light to study objects. I spend almost no time thinking about X-ray and radio astronomy, but it should not surprise you that for observations of the same galaxy, for in this case, Centaurus A, that it's really only when you combine observations from all of these forms of light that you're able to get a complete picture of this galaxy, right? And so if you just look at here, that you have this composite picture where you see, for example, the jets and everything else here. And so for this talk, though, while indeed I'll be talking about light for a portion of it, I'm at least going to start with a different messenger, one that often for many of you, you might be a little less familiar with. And to give some context here, we have to start with Newtonian gravity. And so, of course, the story with Newton goes that when he was thinking about the reason that objects fall, that he was sitting under an apple tree one day and apple fell down and struck him in the head, which gave him the idea for how gravitational fields work. And so back in near the end of the 1600s, Newton came up with his famous equation, F equals ma, and in the case of gravity, you have F equals g m1 m2 over r squared. And this has been largely successful at explaining gravitational phenomena over the last 300-400 years or so. And it's what we've been relying on for very much of that time to understand how the universe works. And so, of course, gravity is it governs many of the objects in our galaxy and the universe and the way things work. However, in many ways, it's our weakest force, right? So there are four fundamental forces: gravity, electromagnetic, electrodynamics, and then the strong and weak forces. And in many senses of the word, gravity is incredibly weak. And so if you look on this last slide, you see this big G out front with our equation here, and this term is known as Newton's constant, and it's something like 6.67 times 10 to the minus 11 meters cubed per second squared kilograms. This is a very, very tiny number, and so it really only becomes relevant when the masses become very, very large. And therefore, gravity only really becomes noticeable when you're dealing with very large masses. You know, for example, the sun's keeping planets in orbit, the trajectory of a ball in flight. So relatively large objects that are where there's gravitational effects to be considered. And while this theory worked for hundreds of years and continues to do so in many situations, there are some limits to it. And so there's two that will become very relevant in what we're going to talk about today. So Newtonian gravity works if the speed is small relative to the speed of light. So when objects are moving much slower than 3 times 10 to the 8 meters per second. And when the gravitational potential is small, when you're talking about objects that are not particularly large. And of course, there are situations, especially in astrophysics, where this doesn't apply. And so it was in the early 20th century that Einstein's theory of general relativity came along to supplant Newtonian gravity as our way of understanding how the universe works. And so to give a sense of what Einstein says, we'll start with a quote. "Nothing in the universe can travel faster than the speed of light, including information on the distribution of mass." And so it was this realization that information cannot travel infinitely fast. For example, if the light that we receive from the sun takes something like 7 minutes to reach here on Earth, that information, if, for example, the sun was to blow up, we shouldn't know about it for that period of time because information travels at that rate. And this leads you to the concept of space-time, which is this really funny thing. But the way that I like to think about space-time, or the way to think about gravity according to Einstein, is where you think of gravity as our universe being on some kind of rubber sheet, right? And so you can imagine you have a rubber sheet, and perhaps that you have some kind of marble in the center of that rubber sheet. And it's really the deformation of that sheet that, for example, if I was to roll marbles on that same sheet, those marbles infall towards that marble at the center. And so it's really, these gravitational effects are really mass bending space-time and objects then infalling towards those objects. And so this gravitational force is really just the manifestation of objects traveling in this curved space-time manifold. And so, and of course then the heaviest objects, things like the sun, the earth, etc., bend space-time more than lighter objects. So this brings us to the concept of gravitational waves. So if we go back to our rubber sheet analogy, or maybe better is where we take water in a pond and we have waves in a pond. If I was to toss a rock into that pond, I will get ripples in that pond, right? I have disturbed the surface of that pond. Similarly, if I was to take my rubber sheet and I was to roll a marble across it, I will get little waves in that sheet. And so we can think of gravitational waves as energy that's being distributed due to changes in the distribution of matter on our rubber sheet. And of course, in astrophysics, we're predominantly interested in these large effects like we were talking about. So things like when stars explode, when stars collide, or when stars are spinning very rapidly. However, for these gravitational waves in space-time to have large amplitudes, a lot of matter has to be moving around very quickly, right? So while it's true that me walking around, hopefully not too much here on stage, does produce gravitational waves, astrophysically, to have any hope of them having an effect that we could detect, a lot of matter has to be moving very quickly. And so the idea of these gravitational waves is that they're producing strain. And strain is defined as the change in some path over the length of that path. And it's perpendicular to the direction of propagation. And so if I was a gravitational wave that was moving this direction, I would be expanding space in this direction and contracting it in the other as I move through space. So it's kind of doing this as I walk along. So for gravitational waves, as I said, so they're compressing space-time in two directions, and we call those two directions polarizations. And informally, we know them as plus and cross. So if we look at the figure here, so H plus is kind of the standard one. So I start with a circle, I compress it in this direction, circle, and make an ellipse this way. Cross is simply where I start with a circle, make my ellipse kind of as a cross, right? And so you have these two independent polarizations. And so both of these polarizations, they're both time varying, and their amplitude, or the size of the gravitational waves, depend on the nature of the source that's emitting those gravitational waves, which is how we'll learn about those objects. And so, as I said, in order to produce appreciable gravitational waves, we need to be thinking about objects that have a lot of mass. And there's two particular kinds of objects that come up a lot when we're talking about gravitational waves. So these are known as neutron stars and black holes. So neutron stars are stars that are purely made up of neutrons, and they survive due to degeneracy pressure of neutrons. They have something like 1.4 to 2.3 times the size of our sun. Black holes, which I expect everyone in this crowd has heard of, tend to be larger than three solar masses. And at least in gravitational waves, we've discovered black hole binaries up to about 100 solar masses. And of course, there are black holes at the center of galaxies that are many millions of solar masses. And so these are the kind of objects that are both compact and large enough to produce gravitational waves that we might detect. So what causes these gravitational waves? So the first type that I'll talk about are collisions. And so these are in the form of either neutron star or black hole binary systems. Something like half of the stars in the universe are found in binaries. And so these are objects that are reasonably common that we might expect. And so the idea here is that you take these two compact objects, either a neutron star or a black hole, and they are inspiraling around one another. Over time, they emit gravitational waves, and they lose energy due to those gravitational waves until they get close enough and finally merge. The second common type are explosions. And so when I say explosions, typically I mean the death of stars, typically very violently. So for example, massive stars collapse and produce what are known as supernovae and long gamma ray bursts. And in all of these cases here, the messier the astrophysical system, the better, because fundamentally gravitational waves are produced by non-symmetric mass motion, right? So if I just have the collapse of a perfectly spherical object, I actually won't emit gravitational waves. However, if I have a highly turbulent event, I can expect to produce gravitational wave signals. And for example, supernovae are expected to not be particularly symmetric and therefore produce loud gravitational waves. The third very common type are spinning stars known as neutron stars, and we call them pulsars. And so these neutron stars are extremely dense, something like 10 to the 17th kilogram per meter cubed. To give you a sense, there's something like many thousands of tons of matter in a teaspoon of a neutron star. And so these are very, very dense. And so these are objects that are only something like 10 kilometers in radius or 20 kilometers in diameter. And so you could imagine squishing the entire Earth into a sphere that's no smaller than the entire Empire State Building. And so these can rotate up to 700 times per second. And so they are very, very rapidly spinning. And so these gravitational waves produced from these objects would be if I had any sort of asymmetry in the system. And actually with the gravitational wave detectors, I'll talk about in a second, while the radii are something like 10 kilometers, we've put limits as to how spherical these objects could be on the order of a centimeter. We know that they're no more ellipsoidal than that. So it's quite strong limits. And so how do we know gravitational waves exist? We've known for many years about binary pulsar systems. And so back in the 1960s, there's a graduate student by the name of Jocelyn Bell at the University of Cambridge, who is working on an array of radio telescopes, basically in the backyard of Cambridge. And she discovered what became known as the first pulsar. And so it was with her radio array that she discovered in a certain direction repeated pulses from what was eventually realized to be a pulsar. And so she discovered the first pulsar system. And so it wasn't too long until the first binary pulsar system was discovered. Later on, it was then realized that one could then search for gravitational wave emission by tracking the period change from these binary pulsar system. So I said earlier on, as these two compact objects are in orbit around one another, they're emitting gravitational waves, and their period is changing due to the loss of energy. And so it was this Holtz-Taylor binary pulsar. So you can see in this plot on the right-hand side here, over decades, you can actually measure the change in period due to the emission of gravitational waves. And what's really cool about this measurement is, so in black here is the experimental data, and the black line isn't a fit, it's just the prediction from general relativity. And so this was one of the many successes general relativity has had in the intervening years. So what's the problem? So we think gravitational waves are all around us. I said that when I move around, I'm producing gravitational waves, which is all well and good. But for the vast majority of processes, the expected gravitational wave strain is very, very small, something like 10 to the minus 23. And so just for some scale here, if I was to take the diameter of a proton and divide by, for example, a 1 kilometer detector, I only get down to 10 to the minus 18. And so I still have five orders of magnitude to go to get to the required gravitational wave strain sensitivities to get, to something interesting. So how do I possibly measure such small distances? And so this brings up the concept of interferometry. And so the idea of an interferometer is I take a laser and I put it through a beam splitter. And a beam splitter takes that laser light and splits it in two directions, half going up and half going through the side. And when something like a kilometer away, there's a mirror, and the light bounces off the mirror and bounces back to the beam splitter. And it does that in both of the arms. And so an interferometer is set up such that if the length of those two arms is the same, I don't get any output at my photodiode here. However, if the path length is different, then I do get output on my photodiode. And so for those who are thinking through how gravitational waves affect space-time, i.e. they're expanding space in one direction and contracting it in another, this is actually the perfect experiment. So one arm length gets longer, while one arm length gets shorter. And so as gravitational waves pass, I can detect that path length using my interferometers. And so here on Earth, we have many interferometers at this point. I'll just highlight a few in this slide. There are two, one in Livingston, Louisiana, one in Hanford, Washington, so two in the United States. There's one in Cascina, Italy, which is known as Virgo. And these are kilometer scale detectors. So the arm lengths here are 4 kilometers long. And so as you can tell from the strain equation, getting very large arm lengths is very useful. And so this has a long history, right? So these experiments were not developed overnight. So back in the 70s, there were professors both at MIT at Caltech who were thinking at least at first independently about how to do this gravitation wave detection. And in the 80s, they started to build prototype interferometers, tabletop things where I can go into my lab and, 1 meter, 10 meter scale type things that I could, build myself with a small group of graduate students. At that point in the 90s, both the LIGO and the Virgo experiments got started once it was realized that very large detectors and therefore a lot of money would need to be spent to build these things. And the first observing run of both LIGO and Virgo were in the 2000s. I myself joined LIGO in 2008 at the very tail end of what was considered then the initial set of detectors. Then the detectors were upgraded in the early 2010s and turned back on in 2015. And since then, we've had a number of new observational campaigns. We've also had a new detector join our gravitational wave network known as COGRA, which is in Japan. There will be another LIGO in India by the end of the decade. And the plan is in the 2030s / the 2040s to build future detectors, Cosmic Explorer and Einstein Telescope. Einstein Telescope in particular, a highlight because it's a 10-kilometer scale detector planned to be built underground. The understanding that it will be something like 10 times more sensitive than the detectors we have now. And so I show here the global array of gravitational wave detectors we have at this point. You can see the 2 in the United States, 2 in Europe, 1 in Japan, and 1 planned in India. And there's actually other planned experiments as well, for example, in Australia. So this brings us to GW 150914, which was the first detection of gravitational waves from a binary black hole system. And so to understand this plot and understand the kind of data that we have, I show in this top panel here what's known as gravitational wave strain. So this is the output from that photodiode in the detector that we just talked about. And so what you can see here is, and I really like this data because it kind of shows physically what's going on. By eye, you can see this kind of low frequency oscillation that gets higher and higher frequency until suddenly the signal disappears. And so physically what's going on is the black holes are in spiraling around one another, getting closer and closer together. The period is decreasing, the frequency is increasing until they arrive at one another, and you get the characteristic chirp or whoop type of effect from these 2 black holes. And so there's a lot of remarkable things about our first detection, but in the middle panel, one of the I did an interview with a famous physicist in our field in the past year, and she works on what's known as numerical relativity. And so at the same time as these gravitational wave detectors were being built, theoretical and computational astrophysics who actually solve Einstein's equations on computers had been simulating the gravitational wave emission from these systems for something like a decade at that point. And so on the underlying the data here in black here is the trace that you actually get from numerical relativity. And when I was interviewing her, it made me laugh because she said something like when she saw the first binary black hole detection, she thought it was insane because she had been seeing that waveform every day for years at that point. And she just thought it was some plot from one of her graduate students. And so again, this was another remarkable win, let's say, for general relativity. So of course then, so this is back in 2015, and Nobel Prizes followed, Ray Weiss, Kip Thorne, Barry Barish, and so on. And it wasn't long before we started to find many more. And so these are sort of joking panels to, there was a huge party after the first one. There was a slightly smaller party after the second one. At some point, by the third one, things had started to get maybe a little bit old. But we were really starting to build up this, this catalog of gravitational waves in the following year or two. And we've had many discoveries since, something like 50 binary black hole mergers and a handful of neutron star mergers at this point. And so to set the stage for to talk about the neutron stars, I'd like to highlight this particular event. So I said that the two gravitational wave detectors here in the US, one in Hanford and one in Livingston, for the first year or two, they were running on their own. And so this gravitational wave network that's been developed worldwide, it's been developing. And so the first detection was just with Hanford and Livingston. And the reason this is important actually is because for a number of reasons. So for example, it's important to have multiple detectors because these are very rare and very fundamentally quiet events, right? So it is actually very difficult because of all of the effects that go around in our detectors, things like earthquakes, magnetic fields, even airplanes flying over, many things can mimic gravitational wave detection. And therefore, we actually want these global networks of detectors because in principle, the likelihood of these noise sources being correlated over thousands of kilometers is very low. But the other benefit is that these systems fundamentally functions like time delay antennae, right? And so by measuring the time of arrival of the gravitational waves, in principle, I can tell you where on the sky they occur by measuring the delay in time for the arrival of gravitational waves. And so with two detectors, I can make a big ring on the sky. And with a third detector, I can tell you where the object is within some handful of square degrees. And so it was a couple of years from the time of our first binary black hole detection before we had our first binary neutron star event. And so there's many reasons to be excited about binary neutron stars. So if you look at the characteristic chirp in this spectrogram, it's something like 30 seconds in duration. So the binary black hole mergers was something like tens of milliseconds. And this is much longer, indicating that we had a much lower mass object. So something fundamentally a little different. And so this event was detected in August of 2017. And it was very exciting because not only were we able to detect gravitational waves, but we were also able to measure electromagnetic emission from this object. And so what kind of electromagnetic emission do we expect? So this electromagnetic emission is known as a kilonova. And so I'll just read the quote of what it means and we'll break it down. So it's the electromagnetic counterparts of compact mergers powered by the radioactive decay of hard process nuclei. So what does that mean? Oof, that's tough to see on it shows up nicer on my slides, I guess. Okay, so the idea fundamentally here is we have in a seed nucleus, we have protons and neutrons. And in these neutron star mergers, we have very neutron-rich environment. So I told you that these neutron stars are just, these balls of neutrons. And so when these neutron stars merge, I have this huge excess of neutrons available. And so there's a process known as the R process where neutron capture can form. And so I get these formations of large, unstable, heavy elements. And so along with any sort of unstable nuclei, I get radioactive decay, which is producing gamma ray photons. And so it's these gamma rays that move out and thermalize the surrounding material. So I have these gamma rays produced, they go out and they interact with the surrounding material, thermalizing it, which sets a temperature scale of something like 10,000 Kelvin for my objects. And so it's this emission which ends up being in the UV to the near infrared. And it's this that I'm observing. It's the radioactive decay of these heavy elements that have gone ahead and thermalized the surrounding material and are then, they have a temperature, and that's what I'm observing with these kilonovae. And so for the first time after our first bioneutron star merger back in 2017, there was a team led by Ryan Foley at Santa Cruz who detected the first counterpart to this particular event using an optical telescope. And so I have a bunch of plots here from the early observations, and the counterpart is marked in the black lines here. And this set off what can only be described as the most intense follow-up campaign that's ever been done in astronomy. And it was detected across all sorts of electromagnetic wavelengths. And so on the bottom panel here, so if I assign some sort of T naught to my gravitational wave detection, 2 seconds later, there was the arrival of the gamma rays from the gamma ray burst. Something like 5 hours later, we put out a localization, i.e. we told the astronomical community where on the sky to actually look for these objects. 11 hours later, Ryan Foley's team discovered the optical counterpart. 9 days after that, the X-ray counterpart was found, and 16 days later, the radio counterpart was found, and it's still being observed in radio to this day. So this was a remarkable event for, in many ways, and now that we understand the rates of these events and the sensitivity of our detectors, it was actually a 1 per 40 year kind of event. So you might ask the question, do we need to wait? And so to understand that, we'll talk a little bit about first the astrophysical modeling that goes into this. So fundamentally, how do we observe counterparts? So I said that these gravitational wave detectors, you can localize signals on the sky using them as just using the time delay, right? I measure a time delay between Hanford and Livingston. This creates a ring on the sky. In the case where I have a third detector, I can make smaller localizations. And so you'll see immediately on this sky map here that for many of our detections, which are 2 detector detections, you get these big rings on the sky, the big bananas on the sky. And in the case where I have a third detection for some of these objects, my localization is much better. And so we've since then been spending a lot of time thinking about what future events will look like. And there's one piece of this that I'd like to highlight. So in these show the last observing run, this next observing run that we're on, and then the observing run after that. By the time that we reach this next observing run, we might have hundreds of events per year. And so we're really moving into a situation where we're going to be expecting a lot of these things. So how do we go about and look for them? So detecting gravitational wave counterparts, so we looked at those sky localization plots, but there's a lot of work that's done to actually go try to identify which of the many transients in the sky is a potential bioneutron star merger. And so there's 2 ways in which this is typically done. One is through the use of wide field surveys, where I take wide field telescopes and take images of the localization. The other is through the use of galaxy targeted follow-ups. LIGO and Virgo and other gravitational wave detectors are only sensitive to our local universe, something like 100 megaparsecs, 200 megaparsecs or so. And so actually we can use catalogs of galaxies. We know most of the galaxies within that localization volume, and actually just go point at those particular galaxies. From there, we get an array of candidates. Within those localizations, we may have dozens to hundreds of candidates that we must parse through. And from there, we need to get follow-up photometry and spectroscopy. Photometry here just means taking more images, potentially in multibands, to identify the counterpart. Spectroscopy is what it sounds like, getting spectra to do classification. And from there, we hope to identify and characterize the counterpart, but it's quite a process. And so if I was to give kind of my own bias summary of the optical time domain, there's a lot of surveys, optical surveys that exist on the sky these days. For example, there's the dark energy camera down at on the Blanco 4 meter down in Cerro Tololo down in Chile. We have Pan-STARRS, which is the 7-degree imager on Haleakala. We have ZTF, which is a 1.2 degree, 1.2 meter aperture telescope on Palomar in California. And in the next couple of years, we'll have the Rubin Observatory, known as LSST, which is a 10 square degree imager down in Chile. All of these telescopes are taking observations of the sky all the time, every night. And so it's really about exploiting these very large data streams to try to identify gravitational counterparts. So what makes it hard? Kilonovae are hard to find. So this is a plot on the left-hand side of brightness. So magnitude is astronomers' funny terms for luminosity, essentially. So objects are getting brighter even as magnitude goes more negative. So don't be confused by that. And then on the x-axis is the time scale. And so you'll notice for supernovae, which are very common transients, things that we find all the time, they are, one, both quite bright, and two, they last for weeks to months at a time. However, our favorite kilonova, or GW17817, you'll notice not only is it fainter than the other objects, it's also fading much more quickly. So it's both underluminous and is only up for a couple of nights at a time, which makes it particularly hard. The other thing that's really interesting about kilonovae, and again, it's due to the production of these R process elements that makes the material more opaque as time goes on. But on the right-hand side here, I plot color. And so as the plot goes up, my object becomes more and more red. And so again, while the supernovae stay, well, they redden reasonably slowly, 17.17, I have this really deep reddening very, very quickly. And so these together all form kind of the fundamental characteristics, let's say, of a kilonova. And so I want to take this opportunity to highlight for a second the opportunities that exist within MIfA and our department when we do follow-up. And so if I was to take the survey telescopes, many of them are in the optical. And so this plot here goes from U band, which is basically for the UV, all the way down to K band, which is out in the near infrared. And the vast majority of the survey telescopes are in the optical here, and generally able to observe just the first part of the event. However, let's see. Okay, so it didn't quite show up. However, we within MIfA have what's known as the Mount Lemmon 60-inch telescope, which is a near infrared optimized telescope. So these are relatively uncommon in the community. The vast majority of large aperture telescopes are really optical systems. And what's really nice about the near infrared is that the counterparts fade much, much more slowly than in the case of the optical. Instead of being available or observable for only a couple of nights, they may be observable up to a couple of weeks. And for this reason, we're in the process of roboticizing this near infrared telescope to do gravitational wave counterpart searches. There's also another problem in the community, and the proliferation of the optical telescopes, these optical survey telescopes, has meant that there's a large number of astronomical transients that are being identified by these surveys. Something like in 2019 alone, and since then we've well passed something like 20,000 new transients identified per year. And yet, when I take an image of something, I don't actually know what the nature of that object is. I don't know if it's a supernova. I don't know if it's a cataclysmic variable or other things that go boom on the sky. And our ability to classify those objects is actually relatively abysmal. We classify, less than 1% or something of the astronomical transients we know about. For this reason, once again, within our department, we're in the process of building a new low resolution spectrograph that we're going to put on the Kit Peak 2.1 inch, designed to do classification are dedicated to doing gravitational wave counterpart classification in the next observing run. Okay, so we've talked a little bit about the global astrophysical modeling. We've talked a little bit about the instrumentation we're building. What is the kind of physics that we can do with these objects? So, so first of all, we can talk about the neutron star equation of state. And so what do I mean by equation of state? So all I mean there is the pressure density relation within a neutron star, or equivalently, how its mass and radius is related. And in theoretical and experimental nuclear physics, there are many, many models proposed for how matter behaves inside neutron stars. Neutron stars are very cool because they are fundamentally laboratories for densities that we just can't hope to approach here on Earth. And so actually they're these really great physics experiments that we can perform to understand nuclear matter. So what's really exciting about these objects is that the tidal deformability, or how fluffy these neutron stars are, affect not only the gravitational wave signals I see. Fundamentally, the tidal effects in these gravitational waves, they'll change the phase of the gravitational wave, so I can actually measure the tides in these neutron stars using the gravitational waves. Similarly, these kilonovae are a function of how much tidal disruption occurs in these neutron stars. And so once again, the tidal deformability they have will affect how bright the kilonova is. And therefore I can do equation of state constraints with both gravitational waves and electromagnetic data. These objects are also changing how we think about cosmology. And so cosmology, or the study of the expansion rate of the universe, has a fundamental tension at this point. And so there are two classic measurements of the expansion rate of the universe. One is using the cosmic microwave background, and the second is using type 1a supernovae as standardizable candles. And the community has a problem right now because those two measurements disagree and people don't know why. They don't know if it's systematics in the experiments, perhaps new physics, which would be very exciting. And so gravitational waves and their counterparts have been proposed as one of the, let's say, solutions to understand what is correct. And so the thing that's particularly cool about these binary neutron stars, as long as general relativity is correct, we can estimate the distance just from the gravitational waves alone. This is because I can predict from general relativity what my gravitational waveform should look like, as you saw in 150914. And by combining that with measurements of the host galaxy for my compact object, I can do Hubble constant measurements. And altogether, by combining the gravitational wave and electromagnetic data, we're already really pushing down the constraints onto scales that are not so far from the existing measurements, which is very exciting. So how can you contribute? So I'll highlight a couple of, let's say, citizen science efforts that we're really excited about. So the first is on the Zooniverse platform. It's known as Gravity Spy. So Gravity Spy is an effort to classify the many both non-astrophysical and astrophysical transients that we get in gravitational wave searches. And so this is actually an opportunity to look at our gravitational wave data and potentially find gravitational waves in addition to all of the other types of transients that we identify. And so we built these website classifiers where you can actually classify the different types of events, which is pretty interesting. We have something very similar going on with the Zwicky transient facility, where you can actually look for supernovae, kilonovae, and other kind of light curves. And so this kind of gives you some insight into the day-to-day lives of multi-messenger astronomers. For those of you who are amateur astronomers yourselves, we've been building a network that we call Kilonova Catcher. And the idea here is that because these events fade so quickly, we have been soliciting help from the amateur astronomy community to follow up our transients. And we've been, during our last observing run, we had something like 40 participants. And now, since then, we've had more than 100 amateur astronomers involved in efforts to classify counterparts in between runs. And so this has been a really exciting initiative, and with the slides, there are ways to understand how to join. So I'm almost out of time here, but I want to highlight something very quickly. So on the far left-hand side here, I have where we stand now. So these are the binary black hole, neutron star black hole, and binary neutron star detections. And you'll notice that the binary black hole number is 50, 100, something like that. As I said, we have some handful of binary neutron stars and neutron star black holes. However, as we move towards to the next observing run, which is kind of in the middle of this plot, and then the observing run thereafter, a couple of years down the line, you'll notice that these numbers are rising to 30, 40, 50 binary neutron stars and more than 1,000 binary black holes per year. And so it's not long before we'll be inundated with objects to do exciting physics, cosmology, nuclear physics, testing general relativity, et cetera. And so it's really about to become, let's say, a mainstream mainstream astronomy by the time in just the next couple of years or so. More broadly for the future, ground-based gravitational wave detectors, which are on the far right-hand side of the plot here, are just kind of the beginning to the spectrum of gravitational waves. For example, right now, there are pulsar timing arrays that these are radio telescopes that track pulsars on the sky and look for correlated deviations in their pulses to try to detect a low frequency stochastic gravitational wave background. So that's going on right now. Also going on now is CMB polarization studies, and there are others in MIfA who work on this, who look for imprints of gravitational waves from the inflationary period, from the Big Bang, to do gravitational wave searches, and that's yet a very currently another very popular field. A field that's about to explode in the next few decades is space-based gravitational wave detectors. And so this is an experiment that's known as the Laser Interferometer Space Antenna, or LISA, that will do millihertz gravitational wave astronomy. So the idea here is you'll have a series of satellites, once again, that function kind of like interferometers, where you have laser beams going back and forth between these satellites, but at tens of millions of kilometers spacing. And so you can do really low frequency gravitational waves. These are particularly cool because they will be able to study for the first time, for example, the merger of very, very large black holes, kind of supermassive black hole type mergers. And so anyways, I hope I've convinced you that this is a growing and thriving field, and it has a decades-long future ahead. And yeah, otherwise that's my talk, and thank you all for attending.